and you recall from previous presidential campaigns, concerns about the growth of the national debt. It's growing exponentially. We'll also see later on there are things that fall off, that reduce exponentially. For example, one example I want to give now is what's called a learning curve. Let's say, for example, right now I gave you a list of 50 gibberish words. That is, words that had no meaning. You learned the word, you memorized the word, and probably if I gave you enough time you could have memorized all 50 words. Let's say later on today I gave you a test to write as many of those words as you could remember. You probably would remember most of them. And then tomorrow I gave you another test, and next week another test, and next month, and in 6 months, and in a year, and 5 years from now. And pretty soon you'll see that you'll lose most of those words. In fact, by another week from now, you'd probably have forgotten most of those words if you haven't had a chance to look at them. And after a while, what would happen is you'd probably be down to 1 or 2 words that for some strange reason you continue to remember. That fall off of your knowledge of those words would be an exponential function, as we'll see later on. But before we go in and look at exponential functions and how to sketch them, and exponential equations and how to solve them, what I want to do is review some ideas about exponents that hopefully you learned way back in 7th or 8th grade, that you've used in Algebra 1 and you're familiar with, but just to be sure, because sometimes things kind of slip to the back of the old brain, I want to remind you of those. Let me take a sheet of paper here so I don't forget any, and talk about properties of exponential numbers. Let me go ahead and erase this. This is, again, the base form of the exponential function. How about this? We take the base b, we raise it to the m power, and we multiply it by b to the n power. Hopefully you recall that rule says that when the bases are the same, you keep the base and add the powers. Quite frankly, I am not going to take the time at this point to show you why these work. If you don't know why these work, you should find out, because there's a reason for each of these rules. But again, we don't have the time here. This really goes back to pre-algebra skills. If you divide two numbers with the same base, you keep the base and subtract the powers. And by the way, these rules will come into play in our next lesson. We talk about logarithms, which are the inverse functions of exponential functions. So it's a good idea to write these down just to make sure you have them under control. We also know if we take the base and raise it to a power and then raise that to a second power, another power, that we multiply the powers. That's b to the mn power. We multiply the two powers. We also know that any base to the 0 power is 1. Now, I realize for many students this makes no sense, because you'd say, well, anything to the 0 power should mean I have none of these b's, and therefore I should be 0. But it is 1, and again, if you don't recall why, you might even ask your teacher or look back at an old pre-algebra book to find out why. It's my belief that the students, again, should know why, but you should know this. This is important. And the last of these rules is that if you have a negative power, b to the negative m, that is the reciprocal. The negative power is the reciprocal, and that's 1 over b to the m power. And for example, some numerical examples here that we could see, let's say 3 to the second times 3 to the third would be 3 to the fifth. 4 to the sixth divided by 4 to the fourth would be 4 to the second power. If I had 5 to the second to the third power, that would be 5 to the sixth, since 6 is 2 times 3. Anything for, well, 17.38 to the 0 power is 1. As I like to say, your social security number or telephone number to the 0 power is 1, because anything to the 0 power is 1. And for example, 8 to the negative 2 power is 1 over 8 squared. Okay, so that's a quick review of some ideas about using exponential notation. Quite important, because we're going to be able to use those as we solve exponential equations and as we sketch the graphs of exponential functions. Let's take a look at a very simple exponential function, and we'll do that at the easel. Let's take a look at y equals 2 to the x power. Again, it's an exponential function. You have a base of 2, and the x is in the exponent. Okay? And we're going to sketch this just as we did other type things by plotting points. I mean, if we don't have any idea necessarily what this looks like, it's probably a good idea to plot points, get a feeling for what the graph looks like, and then use that knowledge to graph other exponential functions. So let's go ahead and put axes in here. And let's go over here and set up a little table. X, Y. Let's start out. Let's put some negative numbers in. How about negative 2? Negative 1, 0, 1, 2, and possibly 3. Okay. Let's see. And what I'm going to do here is I'm going to allow each of these boxes to represent 2, so that the 2, 4, 6, 8, etc. And I'm going to do the graph in another color in black so we can see it very clearly. Now, what happens when x is 2? What is 2 to the negative 2? Remember, the negative power means the reciprocal, so 2 to the negative 2 would be 1 over 2 to the second, or 1/4. Put that in here. And plot the point. When x is negative 2, y is 1/4, right here. Notice we cannot raise 2 to a power and get a negative number. It's impossible. So we're never going to get a negative number. We put in negative 1 for x, we get 2 to the negative 1, which is 1 over 2, which is a half. We put in 0, we know that 2 to the 0 is 1. 2 to the 1 is 2. 2 to the second, or 2 squared, is 4, and 2 to the third is 8. So let's plot those points. Negative 1/2 would be someplace over here. Make a little bigger dot. 0, 1 over here. 1, 2. 2, 4. And 3, 8. Now notice what happens. As the points move to the right, they go up faster and faster, and that's exactly what happens with an exponential function. It grows up faster and faster, rising exponentially. What happens back here? Well, can we raise 2 to a power and get 0? No. Let's put in a very, very negative number, 2 to the negative 1,000th power. That's 1 over 2 to the 1,000th, a very, 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 very small positive number, which means this graph will get closer and closer and closer, but never touch the x-axis. And therefore, the x-axis is its asymptote. Again, close, but not touching. So it looks like a typical exponential function starts off very slowly, rising very slowly, and then all of a sudden grows rapidly. A good example of that is, for example, a new product. Someone brings out a new product. Very few people hear about it at first, so the sales are rather small. Then those people start telling their friends, the company starts advertising, people hear good things about the product, and what happens? Sales grow. And the more they grow, the more people find out about it, word of mouth spreads, the company is making money, so they have more advertising, and they're selling more product, and the growth is phenomenal. Unfortunately, for most stockholders and business owners, this doesn't happen forever. But at least in the initial part of the product development, this is what you hope. If the product is to be successful, it's going to grow. Its sales are going to grow exponentially. So this here is y equals 2 to the x. We're going to look at some other graphs right now. Let's look at the next visual, which should show us y equals 2 to the negative x. Okay, now remember, y equals 2 to the negative x. We can know that should be y equals 1/2 to the x, but to prove it to you, on this visual, I have an intermediary step that says if 2 to the negative x can be written differently, it can be written as 2 to the negative 1 to the x. Remember, when we raise a base to a power, we multiply powers. And therefore, 2 to the negative 1 to the x is 2 to the negative x. And 2 to the negative 1 is a half. So another way of writing 2 to the negative x is 1/2 to the x. And let's see how we graph that. The next visual shows us a roster of points for 1/2 to the x, which of course also could be written as 2 to the negative x. Notice now when we plug in x is negative 2, 1/2 to the negative 2, well, that says take the reciprocal of 1/2, which is 2, and raise it to the positive 2. So the answer is 4. So as x gets more and more positive, notice the values of y become smaller, but they never become negative, because we cannot raise a positive number to a power and get a negative number. In fact, we can't get 0. Let's look at the next visual, which has the sketch of those points connected with a curve. Y equals 1/2 to the x, or it could be written y equals